So we've talked about rates in class and how to determine this rate expression from using the integrated rate law, which includes time, and from the differentiated rate law, which is where we do the table logic to figure it out. So we haven't talked about what the orders mean. So now we're going to finally talk about what do these powers mean. So you'll notice we have the equation NO2 plus carbon monoxide makes nitrogen monoxide and carbon dioxide. And we can experimentally determine the rate law as K times NO2 to the second power or second order. So you'll notice there's carbon monoxide in the reaction, but how fast it's going is not dependent on how much carbon monoxide there is. Okay, so this would be like we look at the table logic and we'd see we change the concentration of carbon monoxide and the rate is not changing. Okay, carbon monoxide isn't in the rate expression, so it's not affecting how fast it goes. So a scientist sees that and then says, okay, what the heck, I have to explain this. So they propose something called a reaction mechanism. So this is the overall reaction, but there's maybe steps along the way to get to this overall reaction, like NO has to hit in a certain way some other molecule. Okay, so before I go into more detail, I'm going to give you a little analogy about a reaction mechanism. And it would be like, say your reaction was going from home to school. Okay, so we know that you could get from home to school by going this way or by going this way. There's many ways to get there. The overall reaction would be home to school. The reaction mechanism would be what were the steps that you took to get there. Okay, so the rules that help you determine the reaction mechanism is they have to be logical. Like you can't go all the way to the Washington Monument and then come home and then go to school in the same amount of time. Like that's not a possibility that it would do this thing and then, which is insane, and get to school in the same kind of rate that the simple path would be. Okay, and the other thing is that you can't go like from home and then just end up over here. Like your reactions have to add together to give you the overall equation. Okay, so let's look. They have a proposed mechanism right here. So it would be two NOs have to first hit each other and form the NO3, which is what we're going to call an intermediate. Okay, we know it's an intermediate because it's not in the overall equation. The NO is, so the NO is not an intermediate, but NO3 is an intermediate. And then the second step would be NO3 combines with CO to make the final products. Okay, notice that the intermediate goes away. It's no longer there because it's on both sides. And when we add these two equations together, you can very clearly see that we're going to get the overall equation. So the question is, what is the rate determining step? We always say the rate determining step is the slow step. And just by looking at it, I can tell that this is the slow step because my rate has been determined by two NOs. And the only reaction that has two NOs is this one. There's two NOs there as the reactants. So I'm going to show you one more equation. Well, in this example here, maybe two more. In this example here, we have the NO2 plus the F2, and they propose the reaction mechanism, and they say, is it acceptable? So the first thing you need to do is add them together and see if you get the overall, which clearly you do. And then it says, does it fit the rate law? It's the second thing you need to check. So do they add together and does it fit the rate law? So it tells me the slow step has NO and F, and I look at the rate law, NO and F are the two things that are going to determine how fast it's going. So this is a valid reaction mechanism. Okay. I'm going to cut it here and do some other example problems based on your homework.